Oh, perfect. Okay. Hello, everyone, and thank you for coming. And I know this lecture in particular has been um, a roller coaster of technical difficulties, but I'm glad we finally made it. Um, anyway, a little bit, well, thank you, Dr. Pennington, for coming and talking to us today. And a little bit about Dr. Pennington is that, well, he will be talking to us about quantum information. He received his PhD from Stanford in 2020, and he now works as an assistant professor at UC Berkeley. His research focuses on quantum computing and quantum information, which studies how to store information using quantum systems, as opposed to traditional methods that use binary code. And in this regard, he studies how Hawking radiation stores information after black holes have disappeared. So, without further ado, please welcome Dr. Penington.
Okay. Okay, so hopefully technical difficulties work out okay this time. Okay, so I was going to talk to you guys a bit about research I've been involved with to do with black holes and how information gets out of them. But I thought I'd start with something a bit more down to earth, namely an egg. And we're going to take this egg and then we're going to drop it and it's going to hit the ground and it's going to splatter as eggs tend to do. And then we're going to stop time. We're going to take every particle of this splattering egg and we're going to reverse the direction that each of them is going. So now rather than splattering apart, it's sort of splattering back together. And then finally, we're going to start time again. So what's going to happen? Well, the answer is, in fact, something like this. The egg is going to splatter back together. Everything's coming inwards. It's going to hit together in just the right angle. So it merges into a solid object. All the momentum comes together and pops the egg upwards into the air. So what's going on here is that the laws of physics at a very fundamental level are what's called reversible. They run the same way, like evolving forwards in time as evolving backwards in time. All you have to do is change the velocities of all the particles involved and technically do some stuff involving turning electrons into positrons and taking a mirror image of the universe and things like that. But we won't worry about that part too much. The crucial part is that you can evolve forwards and you can roll backwards, and it's sort of deterministic in both directions. This tells us something very interesting about what happens to information in physics when we evolve time. And so what it tells us is that if the laws of physics are reversible, then information can never be truly destroyed. So let's say I have some book, whatever it might be, and for some reason, I really want to destroy the information in this book. I want to erase it so that nobody will ever know what I was reading. No one will ever have the opportunity to read this thing in the future. So how might I go about doing this? Well, in practice, something I might do is I might take this book and I might put it into a shredder, right? And then the book will get torn up into tiny little bits of paper. And in practice, probably nobody's ever going to work out what I was reading. It's all going to be fine. But in principle, with sufficient effort, if the NSA or someone decides they really, really want to know what I shredded, then they could glue together all the tiny little pieces and they could rebuild the book from scratch. It would take some huge amount of effort, but they could do so. So the information's still there. It's just a lot less accessible than it was before. Okay, so maybe I want to step up my game. I really don't want the NSA to be able to do that. What could I do? Well, I could take this book and I could just burn it to ash. Okay, and at that point, for all possible, imaginable practical purposes, then the information has been totally destroyed. There's nothing left but a pile of ash, some slightly hotter air, some photons of radiation streaming off into space, and the information's really, really gone.
Oh, can I just keep for 1 second? Yeah. Logistical issues. Any chance you can make me co so I can let people in as
Sorry, say that again.
Speaking. Any chance you could make me co-host so I can let people in as you're speaking?
Yeah, let me try to. There we go. This should do. Okay, cool. Hopefully that works. Okay, so in principle, even though we burned the book isn't left, then the information in the book is still there, and it's stored now in the states of all the air molecules that got heated up, and the light and the heat that got emitted, the exact state of the ash left behind, and so on. In principle, depending on exactly what was written in the book, then that will all be in a slightly different state. And so in principle, the information is still there, it's just completely impractically inaccessible. Okay, so now let's say we want to really step the game up. Take this book, fly off however many light years away the nearest black hole is, and we throw the book into the black hole. So now, obviously in practice, that will again stop anyone ever finding out. But back in the 1970s, then Stephen Hawking made a deeper claim about what this says. He said that if you wait long enough, then eventually the information thrown into the black hole will just genuinely vanish from the universe. It just won't be there anymore. There will be no way, even in principle, for anyone to ever work out what happened. So this is telling us something very radical. It's telling us that the dynamics in quantum gravity, this relies on having both black holes, so gravity, and also having quantum mechanics to get the effects Hawking's talking about, just not reversible. This process of evolving forwards in time can't be undone by then evolving backwards in time. So this was a very extraordinary claim, had a huge influence in physics in the 50 years since. And his argument was the following. What he showed is that quantum mechanically, black holes aren't quite actually black. They're more like a very, very, very dark gray. So they actually have a very slight glow to them. It's not a visible light glow. It's more like a glowing slight amount of radio waves. But they emit some small amount of electromagnetic radiation, and also other sorts of radiation like gravitational waves and so on, but in particular electromagnetic radiation. And this radiation carries energy, which, because energy is conserved, means that the black holes lose energy. The black hole gradually evaporates and gets smaller over time. Moreover, he claimed that this radiation coming out is actually in a totally random thermal state. It's just like random noise, random radiation that has nothing to do with the state of matter that fell into the black hole. So say the book and some stuff that I threw in has no effect on this radiation. Eventually, the black hole fully evaporates. We have no black hole left. All we have is this random noisy radiation, but that doesn't know anything about the state of the matter that originally fell in. So apparently all that information has just been totally lost, and there's no way for us to find it out. So when Hawking claimed this, it immediately made a lot of people really, really unhappy. They sort of said, you know, how on earth can this be the case? This isn't how physics works. This isn't how every other law of physics that we know works. And over the next 45 years, there was sort of increasing evidence that Hawking was actually wrong. So that rather than being totally random, Hawking radiation just sort of looked random, but actually wasn't really. It's like when you generate a random number in your computer, it looks like it's spitting out some totally random number, but in reality, it's only what's called pseudo-random, meaning it's very hard to tell that it's not random, but really it's some deterministic process producing it. So secretly, the Hawking radiation is actually encoding all the information that fell into the black hole. It is still there. It's just really, really hard to see. Just like when we burned the book, the information was still there in the aftermath of the burnt book, but it was very, very inaccessible. So in 2019, we finally had a sort of big, exciting breakthrough that involved me and a load of other people now in the corner here, where for the first time, we could actually directly see that Hawking was wrong rather than just giving indirect evidence that he couldn't possibly be right. So we had the first quantum gravitational calculations that showed information escaping the black hole. So ideally, I'm going to try to get to giving you guys some sense of how that happens, how that works by the end of this talk. So we now know Hawking's mistake. We know how we screwed up. We know why this radical claim he made that quantum gravity is different to every other law of physics isn't actually true. Okay, so to get there, we're going to need to cover quite a lot of stuff. I'm going to cover it all at a very high level, but hopefully give you guys a sense of how it all works. We're going to start with a bit of thermodynamics. So I showed you this video at the beginning of an egg forming back together, re-solidifying, unbreaking, and popping into the air. And that video probably looked very weird. It's not something you see in practice in real life. I just made it by taking the first video and playing it backwards. I didn't actually unbreak an egg, obviously. So why doesn't it happen in real life if in principle it would happen if we reversed all the directions of the particles, as I said? Well, the answer is that to be able to do this, we need to reverse the velocity of every single particle. If we just missed a few of them and they were still going the same directions before, then rather than reforming into a solid object, the egg will just sort of splatter back together and then fall apart again on the ground. It won't perfectly reform into something solid. And the reason for this is that there's some very large number of possible states that basically look like a broken egg splattering apart, right? There's all the different little bits of egg. They're all doing different things. And from our point of view, they all look what we call macroscopically indistinguishable. They all just look like a splattering egg. But really they're different states of the egg. And there's a general rule in physics that says that only a tiny fraction of these states can possibly reform into an unbroken egg when we evolve forwards. And this is that the entropy of an unbroken egg is much larger. Sorry, the entropy of a broken egg is much larger than the entropy of an unbroken. So what do we mean by entropy here? So we first need two different notions. We need the notion of what a microstate is and what a macrostate is. So a microstate, just the complete microscopic details of a particular state of some system, of our egg, right? So that includes things like the position, the velocity of each individual molecule in the air and each individual molecule in the egg yolk splattering apart and so on. And then there's the notion of a macrostate, which is sort of the macroscopically significant details about the state. So for example, with the air, it would just be the temperature and pressure. With the egg, it's just roughly how it's splattering. And then there's this famous formula due to Boltzmann that says this thing called entropy of this particular macrostate, so the entropy of the air at a certain temperature and pressure, just given by the logarithm of the number of different microstates that correspond to that same macrostate. So for example, for a broken egg, this is very large because there's all these different possible states that correspond to the same macroscopically splattering egg. In general, this n is like really, really big for everyday objects. There's a lot of molecules in the air. It doesn't really matter what they're all doing. So it gives this very big entropy. And the second law of thermodynamics just says that, look, the laws of physics are microscopically reversible, as we said at the beginning. That means different initial microstates have to lead to different final microstates. If I start with two different initial microstates in my system, I evolve it forwards in time, they can't end up going to the same one, they have to go to different. So let's say we start off with some macrostates in macrostate 0, which has n0 microstates to it, some very large number. Then we end up with macrostate in macrostate 1, which has some smaller number of microstates associated with it. The probability that that process happens, right, the max number of initial microstates in this macrostate that could end up in macrostate 1 is n1, right? Because it has to be reversible. So it can only be as many as the number of microstates in the state we end up in. But that means out of all the n0 initial microstates we could have been in, only n1 of them could have led to that outcome at most. So the maximum probability of that process happening, conditioned on us starting in macrostate 0, is n1 over n0. Or in terms of entropies, it's e to the entropy of macrostate 1 minus the entropy of macrostate 0. If the entropy of the final state is much smaller than the initial state, this very quickly becomes a very, very small number. So it's almost impossible for it ever to happen. And in practice, this means that entropy essentially always increases. This is the standard statement of the second law of thermodynamics. Entropy always goes up, it never goes down. but it's really just a statement about probability. It's saying that if you start in one large set of states, only a small number of them can go to this later set of states. It's very unlikely that you're in one place. Okay, that's some thermodynamics. We're rushing through fields of physics here. We also need some quantum mechanics. But before I start that, any questions on what I've said so far? If so, please shout.
What's the exception for entropy? Like if entropy decreases, then like what's the result?
So if it decreases by only like 1, then that's not that weird, right? That could happen with probability, 1 over e, right? So about a third or something. But if it decreases by 10, then it's 1 over e to the power 10. That's maybe 10,000, 100,000, something like that, off the top of my head. And in practice, the sort of numbers that we're talking about here for entropies are like 10 to the 20 something for like everyday objects. So if the entropy of this thing is half the entropy of this thing, the difference between them is like 10 to the 20 odd. E to the minus 10 to the 20 is like 10 to the 20 zeros followed by 1, right? It's an incredibly small number, so it just never happens. So there's always some chance it can happen, but it gets incredibly unlikely, and very quickly it just becomes totally impossible. Okay, let's do some quantum mechanics. So there's a famous thing in quantum mechanics that you might have heard of, some words you might have heard, people call spooky action at a distance. Some Einstein quote originally, and it's often quoted in media articles about quantum mechanics, and you might have heard something along these lines. But there's this thing called quantum entanglement that involves information traveling faster than the speed of light. So what happens roughly, people will say that you measure one particle and instantly an entangled particle on the other side of the universe gets affected, even though it's light years away, it's still instant action on the opposite side of the universe. So this story is basically nonsense, as I've said it. I deliberately said it wrong, but it's commonly words you'll hear in sort of popular science treatment of these things. And the reason it's wrong is that measurements in quantum mechanics give random outputs in general. Okay? And so the true statement is that the measurements onto entangled quantum particles will have correlated outcome, meaning if you measure 1 on one side and measure the other side, you'll also measure 1. But that doesn't tell you that you can send information from one side or the other, because it doesn't matter which one you measure first, as long as they both give the same outcome, right? You can't choose what the outcome will be when you measure your one and use that to control the outcome of the other one. It's just the two are going to be correlated to one another, but correlation does not imply causation. So let me just give you an example of how something like this can happen that isn't at all spooky. So let's say I have 2 balls. One of them is red, one of them is blue. I'm going to hide these balls in boxes. Okay, so you can no longer see what's in it. Now I'm going to take one of these boxes and I'm going to fly off in my spaceship to Alpha Centauri or whatever. Okay, so I don't know which ball is in which box. But then when I get there, I can open my box. 50% probability I'll see it's red, 50% I'll see it blue, but it's one color or the other. But whichever it is, I then instantly learn what was in the other box. If I see red, I instantaneously know that if you open your other box, you will see blue, even though you're light years away and there's no way for me to signal to you or vice versa. Okay? But obviously this doesn't involve any information traveling at the speed of light. It's just that these are 2 correlated outcomes from one another that were created by the fact that I took 2 balls in the first place and one of them was red and one was blue. Okay, so this is sort of not weird at all, and it's more similar to quantum entanglement than the words I said on the last slide, but it's still not quite the same. So if this was all there was with quantum entanglement, then it wouldn't be spooky at all. It would just tell us that one of the balls was always red and one of the balls was always blue. And the information was always there, and I just only learnt it later, and then I learned about something far away from me, but I didn't have any information that transferred. So yes, so in that slide, the color of the ball was determined before I left, determined locally by which ball I put in which one, and then they got separated apart in space. But there was nothing weird. The correlation just comes from the fact that I was missing some information before I looked at what was in the box. Unfortunately, the reason, or not unfortunately, whatever, the thing that makes quantum entanglement really interesting and actually quite spooky after all, is that you can show that even if you know everything that you could possibly know about the entangled state, even if it's not like you're just missing some information about which ball was in the box, you know everything there is to know, then it's still the case that you get these correlations between measurements done in here in Alpha Centauri. You still have this weird thing going on. So Einstein had an answer to this. He said, oh, that's just because quantum mechanics itself is missing some information about what's going on, that it's an incomplete theory. It's like a theory that doesn't keep track of what's in the box and then goes, oh, magic, it turned out to be red. But there's a better theory of physics, there's a deeper theory of physics that keeps track of whether the ball was red or blue and knows in advance what the answer will be. So there's extra, this is called hidden information, hidden variables that are the cause of this correlation, that provide this missing information that can give apparent correlation between the two separated things. However, in the 1970s, there was a beautiful argument by John Stuart Bell that said, actually, that's impossible. There's no way to have some deeper theory of quantum mechanics that doesn't have this weird correlation between random measurement outcomes, and that can explain all possible measurements that you can do successfully at the same time. So with the balls, all I can do is look at whether the ball is red or blue. But with quantum mechanical particles, there's lots of different things I can try to probe. And there's no way to have a theory that just has some hidden information like the color of the ball that simultaneously explains all these different things. Okay, so entanglement is genuinely very weird. And entanglement's going to be crucial to what happens in Hawking radiation and evaporating black holes. So yeah, unless anyone has any questions, let's now bring black holes into the game and gravity and see what goes on when. Okay, so the fact about space, fact about the space around us, that even when there's apparently nothing at all there, we're just in the vacuum of space, completely empty, then actually there's entangled quantum fields all around us. So what do I mean by fields? Well, you might be familiar with sort of electric fields and magnetic fields and so on. So those are things in our universe, and our universe is quantum mechanical, so they're really quantum fields. And there's various other quantum fields. Actually, for sort of every particle you can have, there's an associated quantum field. But electric field and magnetic fields are actually the important one. And it's a fact, as I say, that just anywhere in the universe where you have empty space, then quantum fields is sort of neighboring quantum space. So like the electric field at one point here and an electric field at a nearby point here will be entangled with one another, right? So their states will be correlated in this highly quantum mechanical way. So in particular, this is true when one point is just slightly outside the horizon of a black hole, the sort of edge of the region where you can escape the black hole rather than inevitably falling in, and the other one's just inside. Okay, this has nothing to do with gravity, nothing special to black holes, it's just a general statement about the universe. What's special about black holes is that if I let these fields evolve over time, then the field's just outside, able to evolve forward, and the information's able to escape away from the black hole. Eventually just sort of speeds off with the speed of light as photons going out to infinity. Meanwhile, the fields that were just slightly inside the horizon, even though they started really, really close, are never able to escape because the gravity is just too strong. Even light is not able to escape from the black hole, so they remain stuck outside. So what happens is this close, short-range entanglement between just inside and outside the black hole gets pulled apart by gravity into really long-range entanglement that I've drawn here between something inside and something far, far away from the black hole. This stuff far, far away is actually noisy, looks like noisy thermal radiation. It's noisy because it's entangled with stuff inside. So it's correlated with stuff inside, so it has to be noisy if you just look at it on its own. And it carries energy away from the black hole, and this is this famous thing called Hawking radiation. This phenomena the black holes glow very slightly. So Stephen Hawking was actually able to give a precise formula for the temperature of this radiation that I've given here. It's this slightly complicated looking formula that involves the mass of the black hole and various constants. And it's worth pausing for a minute to think about how impressive a calculation this was. It really involved sort of all the major subfields of physics at the same time. So what do I mean by this? So if you see there's this factor, just looking at the formula, you see this factor c here, c cubed. C means the speed of light. So that means that in this calculation, there's inherently relativity getting involved. He was having to take into account the effects of relativity. So this Gn, this is what's called Newton's constant. It's the the Newtonian force of gravity is F equals minus gmm over r squared. This is the G there. So it's telling us that obviously gravity is getting involved. There's a black hole, gravity is important in this calculation. There's this h bar here, this h with a line through it. This is what's called Planck's constant. It's the fundamental constant, the sort of natural constant of quantum mechanics. So this is a sign that this is an inherently quantum mechanical calculation. It did indeed involve entanglement. There's this Kb here. This is what's called Boltzmann's constant. This is the most important single constant in the field of thermodynamics. So thermodynamics getting involved as well. And finally, there's a pi here, so circles are getting involved too. I guess the circles in this case are roughly the black hole is like a sphere. Do with circles. So there was a lot of stuff when this calculation is one of the most beautiful, famous calculations in physics. But the cool thing about knowing this formula is if you know the temperature that a system is radiating out, and you know its energy, the energy of a black hole is basically just its mass by E equals mc squared, then you can work out its entropy. There's some formula relating the two. And if you plug in that formula to get the entropy of the black hole, and as we already discussed, entropy is just the logarithm of how many different states a black hole can be in, we're looking basically the same. Then you get an answer given by this complicated formula. And the important bit here is this factor of a horizon. This is the sort of surface area of this horizon of the black hole. It's the area of the sphere that's the edge of where we can escape from. And there's also this famous factor of a quarter in this formula. So this is really a very quantitative, precise prediction that Hawking was able to make. Okay, so that's what Hawking was able to do. The sort of cool, so that was all worked very nicely. Where things got weird is that Hawking also showed that this radiation is random, as we discussed, because it's entangled with the stuff inside. And if something had been falling into the black hole at the same time down here, that has nothing to do with the state of these entangled quantum fields. So it has the state of this radiation carries no information about anything that fell into the black hole. Okay, so it's just totally noisy rubbish coming out. So this is okay. This is not yet a problem because this is noisy stuff that's entangled with the black hole. And in quantum mechanics, stuff is allowed to look noisy. That's not information loss if it's because it's entangled with something else. It's only when it's the whole system that you're looking at that becomes noisy. That would be a sign that information is being lost and something very weird. Okay, so far, it's all fine, nothing too weird. However, over time, you're going to get more and more radiation emitted. You're going to have more and more of these noisy radiation coming out. More and more and so on. Each of these things carries a bit of energy, so they're also causing the black hole to become smaller over time. Now we have a much smaller black hole with loads of radiation that's come out of it, all that radiation is entangled with stuff that was stuck inside the black hole. Eventually, what happens is that the amount of radiation we have becomes bigger than the entropy of the black hole, which we were able to deduce from this formula involving its temperature and its energy. So there's a general statement about entanglement in quantum mechanics that says that the sort of the randomness, the noisiness that comes from entanglement between two systems is the same for both of the systems. So if system A is entangled with system B and system A looks very noisy, then system B has to look equally noisy. Okay, so if all this randomness was coming from entanglement rather than some fundamental weird loss of information, then this radiation and this black hole should have the sort of same number of different possible measurement outcomes, same number of different possible states. But Hawking's calculation says that the radiation is still completely entangled, completely random state, even when the amount of radiation is much bigger than the entropy of the black hole. That means there just aren't enough different possible states the black hole can be in, according to this formula of entropy logarithm of number of states, to have the same amount of noise as the radiation apparently. So at this point, if we want to believe Hawking's calculation, then we have to give up on information being preserved. We have to give up on this very basic principle of physics that I showed in the video at the very beginning. There's only two options. Either information is lost, quantum gravity is different from every other theory we've known in all of history and how the fundamental principle of how information works in it, or Hawking made a mistake somewhere, and he has to have made a mistake before this time where the amount of radiation becomes bigger than the entropy of the black hole. Okay, so we're steadily getting somewhere now. Getting close to the end. I'm getting close to the punchline. But we're going to need one little more ingredient before we can do that, and that's something called the path integral. So we've already seen that states in quantum mechanics are pretty weird, and they have this notion of entanglement and stuff like that. Turns out quantum dynamics are also pretty weird. So let's think first about sort of classical dynamics. So we're going to have a particle, so some position, and it's moving through time. So I'm drawing time going upwards here, space going right to left. I've just drawn one dimension of space because my screen is 2D. So particles at position x. And in classical dynamics, it always has some fixed trajectory. There's some equations, Newton's laws and stuff that tell you how the direction it goes in is a function of time. So for example, if there's no force acting on the particle, then the particle will just move in a straight line at a constant speed, right? This is Newton's first law. So it starts at point x, it goes at a constant speed through time. Constant speed is a constant angle on this diagram, and then it ends up at point y later on. Quantum mechanics is much weirder. So in one point of view, what happens in quantum mechanics is that the probability of a particle starting at this point A, ending up at this point B, is computed by sort of adding up contributions from all possible paths from A to B. So one thing it can do is just go in a straight line at constant speed, but it could also start off going in the wrong direction and then accelerate over to the right and then back to the left, wiggle around a bit and end up there. And you just have to add up contributions from all of these possible paths. All of them have different sort of weights, that they're weighted contributions in different ways, but we add them all up, and eventually that gives us a number that tells us the probability of starting here and ending up here. And in general, it can start here and end up in all sorts of different places. And that's because a particle in quantum mechanics can be in a superposition of different places.
Can I ask a question about the path?
Yep.
So wouldn't there technically be infinite paths? So how would you add up the probabilities? Like what kind of weighting do you give the path?
Yeah, so you've got to use, adding up infinite things is a sort of standard thing that you do in calculus in integration. An integral can be thought of as adding up all the different points in space. This is a lot weirder than that because you're not just adding up all the different points in space, you're adding up all these different paths. And so this has infinitely many possible points at infinitely many possible times. So mathematically, this starts to become kind of weird. And So for this particular thing, you can make sense of it mathematically in some way. You just have to, yeah, it's sort of, you're adding up infinitely many possible things with infinitely small weight for each of them. So an infinitely small thing times an infinitely large amount can give something finite in principle. Very quickly, a lot of the path integrals that physicists use every day, that I would use every day, mathematicians would say make no sense at all. They're complete nonsense. They're mathematical gibberish. But we use them all the time, and we just ignore the fact that we're doing mathematical gibberish, and we make incredibly accurate predictions. The best scientific predictions in history were done using versions of this calculation that mathematicians would say are complete nonsense. But they're predicting correct answers to experiments to sort of 20 decimal places, insanely impressive stuff like that. So the answer is we don't understand exactly how to make sense of a lot of this stuff, but somehow it does. And gradually mathematicians are making sense of it in more and more contexts, but they're 50 years or more behind what the physicists are doing. So yeah, but it's a great question of how this will make sense. It is, mathematically it's somewhere between hard and impossible, depending on the detail. Okay, so we want to try and do something like this for gravity, because that's the sort of obvious rules for the dynamics of quantum gravity. So in classical gravity, in general relativity, this theory of gravity by Einstein, then the sort of dynamical thing, the equivalent of the position of a particle, is actually the geometry of space-time, the sort of shape and features of space-time, how it's warped and so on. You might have seen this thing of like you put a billiard ball on a trampoline and change shape of a trampoline. That's a very loose analogy, but it's approximately what's happening, that space itself is getting warped by gravity. So that's what's happening classically. And just like a particle, there's certain equations that the geometry has to obey that tells you how matter sort of bends space. So quantum gravity, the sort of obvious rules to apply are that probability should be computed by sort of adding up contributions from all possible space-time geometries with appropriate weights, all infinitely many of them in some complicated way, and using them to compute the probability of something happening, right? That's just direct analogy to what we did to do the quantum mechanics of a particle. And as I said, so even without gravity, then path integrals, if taken too literally, are sort of mathematically nonsense. With gravity, they're probably even more so. There's even more problems with defining it. But if you're careful about what you do and how literally you take this summing over all space-time geometries, then there's controlled approximations that can be made that we think make sense. We have strong reason to think should be computing real controlled effects in quantum gravity. Okay, so we're now finally ready to put that into practice and try to find some controlled gravitational path integral quantum mechanical effect that is going to show us that information actually wasn't lost at all and that Hawking was wrong. So how are we going to do that? Well, what we need is to find some sort of experimental test that can distinguish between some system that's spitting out a totally random quantum state and some system that seems like it's random but equally isn't. So like our computer spitting out a claimed random number, but it's not really. So let's say we had some random number generator on our computer that theoretically is supposed to randomly spit out a number between 1 and 100. Okay. So maybe it spits out 7. How do we know if that 7 was actually random or it's just pretending to be random, but actually it was controlled by some deterministic thing that maybe involved the time of day and some digits of pi or whatever it might be that computers use to claim they're producing something random? Well, with just one sample, just seeing that this thing produced this 7 once, then it's pretty hard for us to tell. There's essentially no way to know whether that was randomly produced or pseudo-randomly. But what we can do is we can make 2 copies of our computer. We can make sure they're in literally identical conditions, and then we run the same process on both of them. And if we run the same process and get 7 on both, then that's pretty good evidence that actually it was pseudo-random rather than being random, right? So if it was actually spitting out a random number between 1 and 100, probability we'd have got the same number in both samples would be the sum over all the numbers between 1 and 100 of the probability of getting that number on the first one times the probability of getting it on the second one. If these are all equal, probability of each getting each number is 1 over 100, then the total for this sum is 1 over 100, right? The chance of getting two the same is 1 in 100 is really small, particularly if rather than 1 in 100, it's 1 and number between 1 and 10 to the 50 or something, which is more realistic for a black hole. On the other hand, if it's pseudo-random, then we'll just guarantee to get exactly the same. Okay, so it turns out there's a quantum mechanical version of this process of doing two samples of the thing and testing if they give the same output. And roughly the way the quantum version of this thing works is you take 2 copies of your state and you swap over the system you're interested in between the 2 copies, and you see if you end up in the same state that you were in before. So it's pretty clear with our 2 computers, if we swap them over and they were both reading the same number, they'll still be in the same state, right? We won't be able to tell that we swapped them over, but if they were reading different numbers, then swapping them over will change the numbers displayed on each screen. It will change which number was on the left and which was on the right. So let's do this with our black holes. So we're going to take all this radiation. We want to see if the radiation is actually in the same state on the left and the right. We're going to take all the stuff on the left and we're going to swap it over with the stuff on the right. Okay, so this looks like a complete mess. But now these sort of these quanta that are inside the black hole and now left black hole are now entangled with things over on the right black hole, and ones on the right are now entangled with things on the left. So naively, this is a very different state than the one we started off with. And in fact, the probability that it's the same state we started with is basically 1 over the number of different states the radiation could be in. Okay, so it's a very small probability, particularly when you have loads and loads of radiation. This just gets smaller and smaller, and the radiation just looks noisier and noisier, more and more random. But now we need to take into account the effects of gravitational particle growth and the fact that in quantum mechanics, space-time can have these crazy quantum fluctuations. We need to add up probabilities of something super weird and non-classical happening. And in particular, it turns out there's something very non-classical that can happen, which is that there's some wormhole going on that connects these 2 black holes. And what that wormhole does, it basically has the effect that it takes everything that was previously in this left black hole interior, goes through the wormhole, and it ends up over on this right black hole interior. Similarly, everything that's on the right goes through the wormhole, and it all ends up on the left. So this is just some process that has to be allowed to happen in quantum gravity because of the quantum mechanical nature of it. And if it happens, then what goes on? Well, now we swapped over all the left interior over here onto the right, and the right interior into the left. And now sort of everything has got swapped between the 2 sides. So now it really does look like we're in the same state we started with, right? Now the left radiation is entangled with left interior, right radiation, right interior. We're back in the same state we started with. So if this crazy wormhole swap just spontaneously happens, at the same time that we try to swap over our radiation between 2 sides, then we get back the original state. So what is the probability, the sort of actual probability of being in the same state we started with after swapping the radiation? Well, it turns out sufficiently late times, when the radiation looks sufficiently noisy, then it's dominated by the probability that this wormhole happens and that the interior of the black hole gets swapped over as well. Magically, turns out this probability is given by e to the minus the horizon area of the black hole over 4 times some constants that I've dropped. It's exactly equal to 1 over the number of states that the black hole can be in. Okay, so remember before we were saying the reason we thought there must be information loss was because the radiation had got more noisy than could be explained by entanglement with the black hole, because the black hole could only be in NBH different states. This is saying when we actually try to do a test of how noisy this radiation is, we don't see that it looks completely random anymore. We get an answer that looks like it can only be in NBH possible states. So exactly the maximum number that could be explained without having information loss. So we just skate by the edge of having any problems, not having any paradoxes. Everything's consistent with normal laws of physics when no information is lost. Okay, so I'm basically going to leave you guys there. That's the punchline. That's the you now know cutting edge. You now know more about what happens to information inside the black hole than any physicist did 5 years ago. But I'm going to end on one note, which is I claimed at the beginning that if we want to avoid the problem, any problems, then information we threw in has to come out. It's not just that the radiation needs to not be too noisy. It also should carry information about the stuff that we threw in. So if we've thrown in this copy of Twilight into the black hole, then somehow there should be a way to look at all this radiation when the black hole is mostly evaporated and learn what was written in this book that fell in. So how do you do that? Well, turns out there's some general purpose quantum algorithm that says, okay, if you have some information and there was some noise, you worried the information got a bit of damage, then there's a general purpose quantum algorithm for correcting that noise and getting back your information. This stuff was developed for quantum computers because people were worried about quantum computers having errors and that breaking the quantum algorithms. And they found these ways of correcting these noise. Roughly, you can think of them as a quantum version of Bayes' theorem. If you're familiar with Bayes' theorem, it's like you try to guess what the missing information would be and thereby get it back. So turns out when you do the quantum gravity calculation, when somebody tries to implement this algorithm on this radiation to try to learn what was written in this book that was inside the black hole, then the very process of implementing the algorithm actually creates a wormhole that roughly, at a very heuristic level, you can think of connecting the black hole to the quantum computer where you're decoding the radiation, where you're trying to work out what this information was. And what happens is that the information in this diary basically gets pulled through this wormhole, and then it comes out and you're able to decode it and learn what it is. So you should not take this too literally, but there is a mathematical calculation that genuinely features a wormhole and the information going through the wormhole and then being decoded, and that's how this process of learning the information works. So yeah, on that somewhat confusing and crazy note, that implementing a complicated quantum algorithm can at least at a mathematical level create a wormhole that pulls stuff out of a black hole. I'm gonna leave it there. I think I've talked to you guys enough. So yeah, any questions then please ask. Otherwise, thanks for listening, I guess.
Thank you so much for talking to us. That was very, very insightful. And mildly confusing, if I may say so myself.
That was the goal. So I hope that you felt you understood something out of it and also found some stuff crazy sounding and confusing, but cool. So if you did, then yeah.
I have a quick question.
Yep.
Yes.
So like at the event horizon of a black hole, when you're having these like particle-antiparticle pairs or entangled pairs being split, how small is like the actual region where that gravitational attraction of the black hole is splitting those pairs?
Yes, so at some level, even if you don't have a black hole, then there's always this entanglement between quantum fields. People will refer to this as like virtual particle antiparticle pairs. I sort of dislike those words. They're not terribly accurate to what the actual math says. It's sort of one way of looking at it, but it's a fairly hand-wavy one. And roughly the scale roughly those things happen at sort of all scales. But the so the further apart they are, the fewer of them they are, and the lower energy they are. So the sort of lower energy modes involved. So I think the real answer to your question is there's a point with Hawking radiation where these things go from sort of being virtual entanglement to actually like real entanglement of sort of virtual particles of what's called vacuum entanglement to being real physical thermal radiation, and carrying energy and so on, having positive energy. And the point where that happens is it's roughly twice the horizon radius of the black hole. More like 3/2 actually, but it's you know, the distance away from the horizon is comparable to the horizon itself. So that's the point where the, you know, to the extent that there's a scale where the Hawking radiation becomes real, then that's the right answer.
Cool. Thank you.
Great question.
Thanks so much for speaking to us. Just wanted to say that.
It was a pleasure. I apologize for previous technical hiccups and so on. I hope you guys enjoyed it. Yeah, I hope you guys go on to study physics and so on. It's a very fun subject. Yeah, there's a lot of cool stuff to learn. You have to take a lot of physics courses before you will cover anything or most of what I talked about here. But the intro physics courses are also very cool, and you will learn at a much deeper level than what's going on than anything I said here, which was, you know, there's no way to listen to the talk I just said and really understand anything I said, because you know, you need an awful lot of maths to actually make it into something coherent and not just some hand wavy words about some magic happening. But yeah, I hope you guys enjoyed it.
I was wondering if I could ask a question. So when you said that information escapes through a wormhole, like, okay, aside from like the math creating a wormhole, when the information escapes, does information come in packets? Like, do you know the velocity and the spin and the charge of something of like all at once, or can you like, or can the velocity of something be like radiated off separately from like its spin and charge?
Yeah, great question. So in practice, generally everything comes out at once. Okay, so this is getting into some technical things, but what actually happens is how long you need to wait to learn. So more and more information comes out the longer you wait. Okay, so for the first long while, then Hawking radiation contains no information, and then once the black hole is roughly half evaporated, then it starts having some information, and then it gets more and more. So an obvious question is which information comes out first, and then which comes out later, and so on. And the answer is that there's no particular bits of information that comes out first and then other stuff later. It's sort of democratic in that it all comes out at the same time. What changes is it's like how long you have to wait to learn information depends on how much information you don't know. So if you knew exactly everything about the state that formed the black hole, like you knew exactly what state the star was in that formed the black hole from collapse, you'd prepared that perfectly in a perfect state and so on. And then there was just one like quantum bit that fell in that you didn't know. And so all you need to know is that one quantum bit. Then you can always learn it basically straight after the black hole is half evaporated. But if there was like 100 bits, 100 different particles that fell in and you didn't know what state they were in, then you have to wait a little bit longer, like 100 times time for a photon to travel around the edge of the black hole 100 times more, roughly, up to some factors. So the more you don't know, the longer you need to wait until you suddenly all at once learn everything you don't know, in principle. Obviously, in practice, it's really, really hard to decode the radiation and learn it. But in principle, the information can be recovered as long as the total information you don't know about stuff that fell in is sufficiently small. If you don't know anything about what fell in, you have to wait until the black hole maybe 95% evaporated, something like that, ballpark. So yeah.
But wouldn't you only learn about the information in a black hole once it evaporates? So like if you found out about all the stuff you didn't know all at once,
Yeah.
how would that work for the black hole? Like would it just like evaporate a chunk all at once, would it?
No. So it's evaporating steadily. More and more radiation is coming out. But it's a weird effect where there's this like critical amount of radiation where suddenly you go from not being able to learn anything much to knowing everything. Even though the new information is just some, like you're using all the information you already had. There's already information there, but it's not useful to you until a critical time, and then at a critical time you can use it to recover everything. But like there is information that's already come out, so it's not like the information is coming out all in one go magically. It's just it only becomes useful to you at a certain time. There's somebody else who knew more information than you could use it to learn some stuff, but you can't really learn anything from it until some critical time when suddenly you can learn anything you want. This all has to do with quantum entanglement and the fact that quantum mechanics is so weird. You know, there's this beautiful, interesting theory called quantum error correction about how, what you can learn from quantum state in the presence of noise. And it's very rich and interesting theory. And it has these very weird effects like what I've just described, where you can suddenly go from not being able to learn anything useful at all to just being able to learn everything all at once. That's you should feel uncomfortable with it. It is weird. There are qualifications to what I just said, but that's the best answer I can give. Okay.
And I was like, sorry, I thought I had one more question. Okay, so I have done very, very little research on this topic before, but when I was researching it, I ended up learning about like the holographic principle. So what exactly about like what you talked about connects to holographic principle? Like how does the whole like wormhole swapping thing connect?
Great question. So a lot, but I wanted to avoid having one too many things, and so I didn't mention it. But okay, so if I go back a later slide. When we originally get this formula that says the log of the number of possible states a black hole can be in is proportional to the area of its horizon, that was the original evidence for the holographic principle. So a normal quantum system, like say some gas or something, its entropy, the log of the number of states it can be in, scales with the volume of the system. So we live in 3 dimensions, so it scales as sort of its radius cubed. What we're seeing is that for a black hole, it only scales as radius squared. This is a very weird feature, but it's actually not just a feature of black holes, it's a feature of gravity in general, because if we try to make a gas to make more entropy than a black hole in sort of the same volume, then the gas would have so much energy it would collapse into the black hole. And so there's just a very general bound in quantum gravity on how much entropy you can put into a black hole that scales like the radius squared. So then people, originally Gerardo Tuft and Lenny Susskind, sort of said, maybe really it's because quantum gravity is sort of like an ordinary theory in 1 dimension smaller. So if we were in 2 spatial dimensions rather than 3, then R squared would be the answer we'd expect, right? So that was their very out there wacky, everyone didn't really believe it proposal. And then in the late 1990s, Juan Maldacena came up with this thing called ADS-CFT, this very concrete proposal for how this actually works. So it doesn't describe quantum gravity in our universe, but it can describe quantum gravity in universes not too dissimilar to ours. And it literally says that there's an equivalent description to quantum gravity that's just ordinary quantum mechanics with no gravity in one fewer dimension. And you can think of it as living at the sort of the boundary of space-time, infinitely far away at the edge of space-time. So yes, so a large fraction of quantum gravity research today involves those theories that Juan Madisina discovered, this thing called ADS-CFT. And in fact, most of what I talked about today was first thought about concretely in the setting of ADS-CFT and was understood there. And then we later realized that it didn't actually rely on being in that setting at all, that you could make sense of it more generally in our universe, for example. But yeah, certainly this is all consistent with the holographic principle and is strong evidence for it and so on. Yeah.
And when you were at Stanford, did you ever listen to Sufkin lectures? Like, did he ever teach you?
I mean, I worked very closely with Lenny. I've written papers with Lenny. I'm currently in an email back and forth with Lenny. You know, I was sending an email to him a few hours ago. Like I've listened to him give popular talks and also technical talk. I've listened to Lenny give many talks. He was sort of my unofficial co-PhD advisor. So my main advisor was Patrick Hayden, who's also a brilliant figure, more of a quantum information person, but also does quantum gravity. But yeah, Lenny was yeah. Lenny at least counts me as one of his students when he lists his students in email. So I guess I sort of count as a student. But yeah, he's a very cool guy. Yeah, his lectures are great to listen to. He's he's a true visionary of just confidently proclaim things, and we'll all be like, okay, Lenny, whatever you say, yeah. And then 5 years later, we all realize he was totally right as usual. Yeah, very cool dude. Any other questions? Okay, well, should stop sharing.